right, so what we learned about before, let me make this bigger. What we learned about before was we were talking about a Taylor polynomial. So we had a polynomial that represented a function, right? And now we're going to take those polynomials and we're going to say that since each term is so repetitive and there's a pattern to it, like, oh, that could represent a series. Does that make sense? So now we're going to talk about Taylor series. And so that's what you can see on your paper is we have that polynomial written out for every term. And then the nth term ends up being like the formula for the series. Does that make sense? So that's what we're seeing right there. If c equals 0, just like before, it's a Maclaurin instead of a Taylor. All right, so we notice this time that I'm using an equal sign, not an approximately sign. And that's because this is an infinite series, so it really does go on forever. And the series equals the polynomial. Like it represents the entire polynomial, okay? So I'm not saying that this series is representative of a function and that it approximates the function like I was before. I am saying that this series exactly equals that polynomial if that polynomial went forever, okay? So I'm going to say this is an infinite series. So it will go on forever, and the series is the polynomial. All right, so example 3 says find the first 4 non-zero terms and the general term. What do you think it means by general term? The nth term. Yeah, the nth term. So circle that, right? Nth term. It's very common for them to phrase it like that and to expect that you find that. That's very common. For the Taylor series, f of x equals e to the 5x centered at c equals 2. Can we use our little shortcut that we should have written on our cheat sheet for this one, e to the 5x? No, because those are all Maclaurin. Oh, do you see the difference? As soon as they said centered at c equals 2, we can't use our little shortcuts anymore, okay? Those have to be centered at 0, then we can use the shortcuts to our heart's content. So this time we legitimately have to go and write the function in the first, second, third, fourth derivative. We have to evaluate all those derivatives at 2. We can only, Maclaurin, it just means you can only use those shortcuts when you're centered at 0. Okay, so that would be something to add to your cheat sheet not to make that mistake. It has to be centered at 0 for you to be able to use those, okay? And I think you probably would have picked up on that when you were doing this problem because you would have realized at no point did you ever use the 2. You'd be like, what did the 2 have to do with anything? And you'd realize at the end you did it wrong. Okay, so we're going to say f of x equals e to the 5x. And so f prime of x is not 1/5, 5 e to the 5x, right? So we're taking e to the 5x and multiplying it by the derivative of the exponent. If you are good at doing that all at once, you can. I always write it like this because that's the chain rule in my head. And then I go, oh, that simplifies to 5 e to the 5x. But you know me, I like to show my work. So if you don't want to do that, that's fine. Okay? And then our second derivative would be 5 e to the 5x times another 5. All right? And I'm going to go ahead and just call that 5 squared. Calling it 25 is exactly the same thing. It's totally fine if you want to do that. Okay? Our third derivative would be 5 squared e to the 5x times 5 again, which I could think of as 5 to the third e to the 5x. Okay, so my next step to find all my coefficients is to take each of these and evaluate them at 2. And so that's the part where, well, that's part of me having that center
You don't
of
have to
2.
do 4.
Oh, no, you're right. I need to keep going. I'm sorry. On my notes, I did not go to 4. That's why.
Oh no.
Whew. You know what happens when I deviate from my notes, then all of a sudden everything's wrong. So, no. Okay. So if we take the original function and we plug in 2, what do we get? E to the 10, okay. And then if we take the first derivative and plug in 2, 5e to the 10. And if we take the second derivative and plug in 2, 25e to the 10, or you could say 5 squared. And then the third derivative,
5 cubed e to the 10.
yeah, I was going to say that there's a little bit of OCD in my brain, and that really hurts me to write it down, but I'm going to do it because I'm growing. I'm growing as an individual, and that's fine. All right, and then 5 to the 4th. No, don't do that to me, you guys. E to the 10. I'm so uncomfortable. I'm sweating.
That's the crust.
That's the crust. That was way too oh, gross. Okay, so now that we have all those written down, what should we do?
Start.
Yeah, we do our formula, right? So we start off with the first one. We've got e to the 10. Plus, do you guys want to do 5 squared or 25? 25. E to the 10, x minus 2 squared over 2 factorial. Okay, plus, we're going to do 125. We're going to be consistent. E to the 10, x minus 2 to the third over 3 factorial. Plus, okay, and then here's how it looks a little different when we do it for a series as opposed to a polynomial, okay? We're going to say plus, and then we're going to do dot, dot, dot to get to our general term, okay? So I've got plus. Now, I have to have a way of representing this number in the front. So we're going to say 5 to the n, right? And that's because this was 5 to the 4th, and it matched up with the 4th. And this was 5 to the 3rd, and it matched up with the 3rd, okay? So we're going to say 5 to the n, then what do we have? E to the 10, and then x minus 2 to the n over n factorial. And then because it's a series and it goes on forever, we don't have a last term. So we write plus dot, dot, dot. And that's us showing it's an infinite series. It keeps going past our nth term. Does that make sense, how we're making it different from that polynomial? Okay, so no end term when we write it as a series. All right, how do we feel about that one? Yeah? It's not a polynomial, so no.
So do we write anything?
No. So this is kind of like, I just wrote out a series. Something plus something plus something plus something plus something. So if we wanted to shorthand this, we would shorthand this by saying, and this is not a bad idea to write in your notes. Our shorthand for this would be the summation from n equals 0 to infinity of this general term. This would kind of be the shorthand. So you'll notice that as we've started writing these particular problems in our shorthand with our sigma notation, we often start at n equals 0, not n equals 1. Okay, so notice that that's our way of getting a term without an x in it to start with. Okay.
So if your writer asks us to do a Maclaurin series or a Maclaurin polynomial,
So we do want to pay attention to the difference between the two. And obviously there's a lot of similarities. You just have to think, Are they talking about a polynomial that represents a function, or are we talking about a series? So here we're talking about a series, which is why we're writing it the way we're writing it. Okay? All right, example 4. It gives us this one right here, and it asks us to find the derivative of the function. So they're saying that this represents the function. They want us to find the derivative, and then they want us to find the derivative evaluated at 0. Okay? So let's go ahead and say we have f of x. Now we're going to find f prime of x. So what's the derivative of 1? 0. What's the derivative of x? 1. What's the derivative of x squared over 2 factorial? So it would be, what would we do with the 2? Bring it to the front. So we would have 2x to the 1, right, over 2 factorial.
We don't do anything to the 2 factorial?
Well, I'll simplify that in a second. I'm just going to show, since it's an example, I'm going to show all my work really clearly so that I understand it later. And then with this one, I'm going to drop the 3 to the front. So I have 3x squared over 3 factorial, right? This one would be, and now this is a typo, that should say n factorial. Sorry about that. So what do we do for the next one? So n times x to the n minus 1 divided by n factorial, okay, and then plus dot, dot, dot. Okay, so that's what we have. Let's go ahead and simplify what we have. So I'm going to say this is 1 plus. Now, if I have a 2 and a 2 factorial, what is 2 factorial? 2 times 1, right? So the 2 and the 2 factorial basically cancel because 2 factorial is 2. So the 2 and the 2 cancel, so that's just an x, right? So here we have a 3 and a 3 times 2 times 1. So the 3 is going to cancel with the 3 of the 3 factorial, and it's going to leave a 2 factorial behind. So I'm going to think of 3 factorial as like 3 times 2 factorial. So that's going to cancel with the 3 and leave a 2 factorial behind. Okay, so give it a second, you'll see it. All right, this one over here, I have n factorial. I'm going to say that n factorial is n times m minus 1 times n minus 2, right? And then it continues. So if I say this n cancels with that n, then this would be x to the n minus 1 divided by n minus 1 factorial. Okay, so look at f prime of x, and then look at f of x. What do you notice? They're the same. What function do we know of where the function and its derivative are the same? So this is the polynomial approximation of e to the x. This is the derivative of the polynomial approximation of e to the x, and it's the same thing. Yeah. Kind of interesting, okay? So what this means is that if we have a polynomial approximation for something, you can take the derivative of that and get the result you're supposed to get. Does that make sense? So the derivative of e to the x is still itself like it should be, okay? If we do f prime of 0, what do we get? We end up getting 1, right, for that one right there, which is the same if we took e, the derivative of e to the x, and then plugged in 0. We'd get 1 for that as well. Okay. All right, that's it for page 4. Oh, I'm going to go ahead and write this, actually. F of x equals f prime of x, and then I'm going to say both are e to the x, or approximations for e to the x. Is that not kind of cool? I think it's kind of cool.
I'm so mad that nobody else thought it was cool during the beginning.
Thank you. Thank you. Joy in mathematic discovery. Air high five. Marvelous. All right, page 5. If we had a math support group on campus, Nancy and I would be like the only people in it.
Oh my god, yeah. And everybody would make fun of us.
Yes, absolutely. They totally would. All right, what we're going to do here, we are going to take that same problem and we are going to find the antiderivative of it, okay? So this represents e to the x. What's our prediction? It's going to become e to the x, okay? So let's go ahead and try it. We're going to take the antiderivative of 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus ... x to the n over a typo again, n factorial. I copy-pasted my typo. So that's unfortunate. And then dx. Okay, are we ready? Let's do our derivative rules, or our antiderivative rules. So the 1 becomes an x. The x becomes 1/2 x squared, okay? The x squared would become, let's ignore the 2 factorial for now. What does x squared become? Okay, 1/3 x to the third over 2 factorial, okay? And what's the next one? Okay, over 3 factorial, okay? And then what would this one be? 1 over n x to the, oh wait, 1 over n plus 1, yes. 1 over n plus 1 x to the n plus 1 over n factorial. And what goes on the very end? Plus c. Ooh, okay. I was waiting to see if you guys were going to kill anything, and you didn't. Thank you, Katie, for saving it. Hedgehog? Was it a hedgehog or a squirrel? I always get those mixed up. I think it's a hedgehog. Hedgehog. Okay. Baby hedgehog did not die today. All right, so we have this. Let's go ahead and simplify it. So I have the x right there. If I take this one, I'm going to move the 2 to the bottom, right? So I have an x squared on the top. 2 is the same as 2 factorial, right? Because 2 factorial is 2 times 1. So I'm going to put, this is 2 factorial. I have an x to the third. If I take a 2 factorial and I put a 3 in front of it, then that's a 3 factorial. Because 2 factorial is already 2 times 1. When I put a 3 in front of it, I have 3 times 2 times 1. So that became a 3 factorial. And this one's x to the fourth. When I take the 4 and move it down, I already had a 3 times 2 times 1. Now I have a 4 with it. So 4 times 3 times 2 times 1 is 4 factorial. I'm going to take the n plus 1, I'm going to move it down with the n factorial. And so what do I have on the bottom now? N plus 1 factorial, right? Because n factorial would be n times n minus 1 times n minus 2 times n minus 3. So if I put an n plus 1 in front of it, then that would be n plus 1, and then n minus 1, n minus 2. So this would be n plus 1 factorial, plus, and then we got our c on the end. Okay, so now what it says is take this, so we found capital F of x, right? This is capital F of x, which is the notation that we used for our antiderivatives when we first found them, right? Tanner, make sure you text that to whoever. Okay, and so make sure she knows, she needs to know. Now we go ahead and we plug 0 in, and we get 1 as an answer when we do that. Okay, so if we think about finding f, capital F of 0, and we plug 0, plug 0, plug 0, plug 0, plug 0, what do we get? C. And when I plug in 0, it equals 1. So the C value is 1. And what does that do to the problem? It gives you the 1 plus in the front. Because instead of having the plus C on the end, we know that's a 1, and we can move it back to the front. So now we can say that capital F of x is 1 plus x squared over 2 factorial plus x to the third over 3 factorial. There should be like cheering and applause. This is like the coolest thing.
So, since we have a plus
Mm-hmm. Mm-hmm. Yeah.
And we're given the f of 0 equals 1.
Mm-hmm.
That's how we know that the plus c is 1 because
Mm-hmm.
when you plug 0 in,
You get 1.
cancels.
Mm-hmm.
Okay.
And so the c must equal 1. So we recognize this function, it's e to the x, and the function in the antiderivative behaved the way we expected to, where we took the antiderivative and it got us right back to e to the x. All right. So now we're going to try this with something other than e to the x. You might think like, that's an exception, so it went from itself to itself. Let's go ahead and try another one. So this one says, use the Maclaurin series for sine x, which is good because we already know that one. So sine x equals what? Maclaurin series, you should have this written on a cheat sheet that you can refer back to.
It's like 1/3. Is it one?
It's not 1/3, it's odd.
Then it's
Does it start with the 1 or does it start with the x?
it starts with the x.
It starts with x because that's x to the 1. Okay, and then,
X to the 3rd.
but is it minus or plus?
Oh my god. Minus. Okay, good.
They're both minus, if that helps.
Yeah.
So x minus x to the 3rd over 3 plus x to the 5th over 5 plus ... And then what was the general form for this one? Anyone remember the general form? The nth term? -1 to the n. X, we had to have the exponent 2n plus 1, it's the one that makes it odd, okay? Divided by 2n plus 1 factorial, and then we do plus ... Okay. So now they're saying take the derivative. Okay, so we're going to go ahead and take the derivative of this. So d dx of sine x, or you could say sine x prime. However you want to write it is fine. So the derivative of sine, we're going to go ahead and say the derivative of x is 1. The derivative of x to the 3rd over 3 factorial. So I'm going to say minus 3x squared over 3 factorial, right? And then what's going to happen with the 3 and the 3 factorial? Yeah, the 3 is going to go away and this is going to become 2 factorial, right? So I'll go ahead and simplify this as I go. Okay? And then the next derivative would be
5x to the 4th over half factorial.
and so the 5 would cancel with the 5, and that would leave 4 factorial behind. Yeah.
So if it's alternating signs, should it after the x then be a minus, or does it matter? Should it be plus?
You can say plus just because you're saying there's more terms. Yeah. It would just happen, you're just adding a negative term next, is essentially how you could think of it. All right, so the only reason you wouldn't put a minus is because I think that would imply that if you put a minus everything after, it might be subtracted, maybe? All right, so then what do we do with the next part? So this is gonna act like a coefficient, so we don't have to mess with that when we do our derivative, okay? The -1 to the n, that acts like a number that's in the front, okay? So all we have to do is we have to take our exponent and move it to the front, right? So 2n plus 1, and then I'm gonna keep the -1 to the n because that's kind of like a coefficient. X to the 2n, okay, divided by 2n plus 1 factorial. And then what happens? Yeah, so the 2n plus 1 cancels with the 2n plus 1, and that's going to leave a 2n factorial. So this is plus -1 to the n, x to the 2n over 2n factorial. So when we took the derivative of sine, we got this as a result. And what is this? It's the Maclaurin polynomial for cos. So the derivative of sine is cos, even when we look at the polynomial approximations. Okay. Okay. And I'm using an equal sign, not a squiggly equal, because technically I'm talking about an infinite series, not a polynomial. So we're talking about series today. Okay. So what we just did is we were manipulating special series, or really any series you can come up with, to show different things. So we found that we can, and we've done this before, substitute into a series for x. So you guys did that the other day when we said if we know what the Maclaurin series for e to the x is, then we could find the Maclaurin series for e to the 2x by just plugging in 2x for each of the x's, right? So we did that. You could multiply or divide the series by a constant or a variable. We did that yesterday when we took the Maclaurin series for cos x and we multiplied it by x to get x times cos x. So we can do that. You can add or subtract two different series together. So if they wanted you to find sine x plus cos x, then you could just take those two Maclaurin series and add them together. The one that I just put in bold is what we just did. You can differentiate or integrate a series. This is the one that kind of slips into problems where you might not recognize that's what they're doing, but that's what they're asking you to do. So I would say like highlight that, put a star next to it. This is the type of one that I think is a little bit less intuitive, but it shows up a lot. And so we, number 5 is to recognize the series as a sum of a power series, which is coming soon. We haven't done that yet. Okay, next page, almost done. Almost done. All right, so this one wants us to take f of x and then take the derivative and take the antiderivative, and it wants us to find the interval of convergence for all of them. Okay, so we're going to go ahead and write f of x, which is x plus x squared over 2 plus x to the third over 3 not x to the fourth, x to the n. Okay, so what's the derivative of this one? 1. Yeah, so it'd be 2x divided by 2, which is just x. 3x squared divided by 3 would just be x squared. Yep, so n to the x, n times x to the n minus 1 divided by n would be x to the n minus 1. Okay? All right, and then the integral of this, 1/2 x squared Mm-hmm. 1/6 x to the third. Mm-hmm. 1/12 x to the fourth. Yeah, so it'd be 1 over n plus 1 times the n that was on the bottom, so it'd be n times n plus 1. Okay, so what they want us to do is they want us to check and find the interval of convergence for all three of those. Okay, so
Do you have the assignment printed in already, or should I print it out when I get home?
I have it, it's just in the copy room.
Just print it out when I get home.
Yeah. All right. Okay, so if we check the first one, we want to find the interval of convergence for x to the n over n. So this is me starting with the first one. And so what's the center? Center is 0, and that's because it's just x. It's not x minus something else, all right? And so now what we have to do is we have to think about if we have x over n, we would think of this as being like a number to the nth power divided by n, all right? And so typically, what did I say the test is we have to use for most of these? Typically the ratio test. So I'm going to go ahead and leave space for the radius and for the interval. Yeah, you could. Unless it was 1, though. Let's do the ratio test. Only because, since we don't know what the number is. Yes. Because what we're doing is we're checking to see what x values you can plug in. And I just think that there's too many, just because we can think of x values that would maybe not quite work with the nth term test. So if we do the ratio test on this, we're going to say the limit as n goes to infinity of x to the n plus 1 divided by n plus 1. And are you guys okay with me doing keep it, change it, flip it already? Okay, so times n over x to the n. So I could rewrite this one as x to the n times x to the 1. So those cancel, and we get the limit as n goes to infinity of x times n over n plus 1. All right. And so what does that limit equal if you plug an infinity in for n? It equals x times 1, right? So the n's would cancel. Those are infinities of the same size. So if this had said like 5n over n plus 1, we'd be like, oh, it equals 5. Or if it had said 3 times n over n plus 1, we'd say, oh, it equals 3. So we're going to say that this equals x. Huh? Okay. So, oh, he can sit right there. He'll be good with Ricky.
If you don't act right, just smack right there. No, I'm not talking to you. Well, come on, give me 10 minutes.
Hey, Ricky, you heard him. If he's not acting right, you smack him in the back of the head. Okay, Ricky nodded, so you should be scared. He smacks really hard. We've seen it. I haven't seen it, that's a lot. All right, so we have an x, right? What do we know about x? And actually, we have the absolute value of x. What do we know about this number that it has to be for this to converge?
0, 1, less than 1.
Less than 1, right? The ratio test has to be less than 1, okay? So that means here that your interval of convergence, or, well, your radius, let's go back. The radius is 1, and the interval of convergence would be from -1 to 1. So the way that I got that interval is I said 0 is my center, I went left 1, and I went right 1, okay? And that's because of this one right here. So that told me my radius was 1. Okay, now this is the part we were talking about that's probably confusing from the video. I know the interval is -1 to 1, but I have to see if I can include the -1 and include the +1. So do you remember what I did in the video to check those? I plugged them in, okay? And then what did I do after I plugged it in? I went back to last unit, and I said if that was a series, would it converge or not, okay? So I'm going to take the -1, I'm going to plug it in for this. So I'm going to say check -1, and when I check -1, that's going to give me -1 to the n over n. So -1 to the n over n. What type of test would this be? Alternating series test. So we're going to do the alternating series test on it. And for the alternating series test, we have to check 2 conditions. Okay, so the limit as n goes to infinity of 1 over n is 0. True or false? True. The second condition is 1 over n. Okay, is that true? Yes. Do you guys know what this test is getting at, this second condition? The terms are decreasing. So another way you could phrase that is if the terms are decreasing, then it works, okay? But we are mathematically showing that they're decreasing as opposed to just saying the words. Okay. So it checked with both conditions, so what's our conclusion about -1? It converges, we can include it. So we're going to go back over here to our interval of convergence. We're going to include the -1. Okay. Now that we've checked -1, we're going to go ahead and check +1. So we have the original problem. I plug a +1 in for x. So I have 1 to the n over n. Yeah, and well, if you think about this, 1 to the n is what? It's always 1. It doesn't matter what you plug in for n, it's always 1, okay? So I'm going to think of this as just being 1 over n. It would equal 0, so the nth term test is not conclusive. That's the one time it doesn't work. But what is 1 over n? It's a p-series. What type of p-series? It's a harmonic p-series, and what do we know about those? They always diverge. So we're going to go back to our interval of convergence, and we're going to say it does not include 1. So when I find the interval of convergence, I am saying if I was to go back in time to last unit and give myself one of these problems, if I plugged numbers in for x that were in between -1 and 1, then those numbers would have made this a converging series, and when I tested it last unit, I would have got converges. If I choose numbers outside of this interval, like if I put a 2 there, or if I put a -5 there, then when I tested it last unit, I would have got diverges. That's what this idea interval of convergence means, is it's talking about if I plug that number in for x, then that specific series would converge or not. Yes?
So we don't want to do that for the other equations, right?
Well, one of the things we learn is that the interval of convergence, the center will hold, I think, but the radius and the interval of convergence may not hold when you go ahead and when you find the antiderivative and when you find the integral. But you guys look like you're dead already inside from doing this. So, yeah, I think what I might do is let you guys work on the assignment for a little bit just to stop taking notes. And then maybe we can go back in a little bit and do the next one and then take a break. And then maybe come back and do the other one just so we can see how they relate to each other without doing them all at once. Does that sound okay? Just because you guys look like you're not enjoying this anymore. Which is fine, because I'm not either. All right. So go ahead and take a mental break.